Okay, hi and welcome to a section of video notes 3.5 on compound inequalities, but this time we're going to do it as a OR compound inequality. And the difference between an OR compound inequality, assuming you watch the AND compound inequality videos that accompany this, is that this one makes either inequality true, or better yet, I should say a solution to a compound inequality that's joined with OR means that it makes either inequality true. We know that compound inequalities are two inequalities. You can see here we've got an inequality and a separate additional inequality. An OR compound inequality means that the solution set, like on the ANDs where they were conjoined, meaning that they made both true, these are the exception. They do not overlap, meaning that it's kind of almost the opposite of solutions or anti-solutions, or the not solution set is essentially what we're finding with an OR compound inequality. Let's see that in action. So this first example here says, write a compound inequality. It represents each situation, and then graph the solution. So here's the situation. All real numbers, and we can identify that as n, we're getting comfortable with that are less than -3 or, there's the key word for us, greater than 7. So let's go ahead and write this portion. So I'm going to write n, and I'm going to say that these solutions are less than -3. That would represent that inequality. I'm going to slap an OR down in between because we need to write that so that it's very clear that this is an OR compound inequality. I'm also going to tag this in as well. So now let's write the right side of the inequality. So it says or greater than, so let's put n is greater than 7, right? So the solutions are greater than 7 or less than -3. Hopefully you're starting to visualize that a little bit, and you can see that that should be not overlapping. All right, so let's identify our variables. Let's identify our boundaries for both sides. Let's start with the -3 here. -3 then is a less than, not less than or equal to, right? Less than. So we're going to identify a boundary. It's an open circle at -3, and we're going to graph this. The solutions are less than, because I'm running into the point first, and -3, meaning that they are going to graph this way. So value is smaller than -3. Or, here's my other inequality, the solutions are greater than, because I run into the open side, than my boundary at 7. So let's identify 7, again, also an open circle because it's greater than, not equal to, and it says the solutions are greater than 7. So what I get is the exact opposite of a barbell. If this was an AND compound inequality, we would be graphing in the middle, but it's an OR. So the solutions satisfies one side or the other, but not both. Okay, on to our next example. I guess it's probably important to say that when we do an OR, we do not combine them. Like we do with an AND compound inequality. So ORs have to be separated by a statement of OR. So in this case, we've got two inequalities we can see here and here, and it's asking us to solve them and graph our solution. We quite literally are going to solve both inequalities separately. So let's go ahead and start that process. So if I'm looking to solve for v, right here, I'm going to start by reverse order of operations, moving addition and subtraction first. So I'm going to go ahead and subtract that 3. I'm going to left with 4v is less than, because those are going to turn to 0, -8. Again, no sign flipping. At this point, I'm going to solve for v by doing its inverse operation, dividing by 4 on both sides. So v is going to be less than -2. Again, no flipping, because we have involved the negative, but we did not divide or multiply by a negative. So very clearly, we are not flipping there. All right, moving to the other side. I'll switch colors. Moving to the other side, here's the v that we're solving for. -2v plus 7 is less than 1. So again, let's go ahead and subtract that 7 off, doing reverse order of operations, leaving us a -2v. Those are now gone, turn to 0, and we're left with a -6 on the right. Now, we are going to divide this -2 away. It's going to turn to 1. But we are now dividing by a negative number to both sides. At this point, and I'm going to switch my sign, I'm going to change its color, I'm flipping the sign. That is the point at which we decide to flip our sign. So I'm left with v on the right, and -6 divided by -2 is going to give me a +3. So, and I'm going to write the word or in here because it needs to be retained so that you know that it's an or compound inequality. So let's graph both of our inequalities. We should find out that they do not overlap or intersect like a barbell. So the solutions then are less than -2. So I'm going to identify my boundary at -2. I'm going to leave an open circle, and these should be less than, meaning I'm shading to the left. On this side, the right side, my solutions are greater than 3. So I'm going to identify my boundary at 3. It is also a less than sign, so it will be an open circle, and it should be the solutions are greater than or shaded to the right. And you'll see that that's not a barbell. All right, my next example then is going to be very similar. Let's go ahead and address this the same way. I'm going to go ahead and subtract 7 to my or compound inequality on the left of -2x plus 7 is greater than 3. I'm going to subtract 7, solving again for that x. Those are going to turn to 0, leaving a -2x is greater than -4 as I combined 3 and -7. Now I'm going to divide by -2 to both sides to remove it from the left, but this is where I'm going to be cautious. I notice that I am multiplying or dividing by a negative. In this case, I'm dividing by a -2. I'm going to go ahead and change that sign, being conscious to make that choice, leaving an x on the left, and -4 divided by -2 is +2. All right, let's do the or statement and solve the other side of this inequality. So over here, I've got 3x minus 4 is greater than or equal to 5. Solving for x, I'm going to add 4 to both sides. I get 3x is greater than or equal to 9. I'm going to go ahead and divide by 3. X is greater than or equal to 3. Again, no flipping, no multiplying or dividing by a negative. Let's graph this and see what it looks like. My boundary is at 2, and it is not included. So I'm going to leave an open circle at 2, and it says my solutions are less than 2, meaning I should shade away from the boundary to the left. And on this side, I'm going to identify my boundary at 3. This time it is included, so I'm going to color it in. And it says my solutions are greater than or equal to 3, so I'm going to shade this way. And again, I should end up with a non-barbell, and I have. All right, thanks for watching the examples. There will be a word problem example that you can additionally watch as well. We'll see you in class.